Hello everyone, I am Gagan Ladha and today we are going to start a very important and basic subject of in mechanical and civil engineering branch, and that is fluid mechanics. Now important in terms of your GATE exam also, and also in terms of your understanding, basic understanding of the subject of the engineering. Now whether you know something about this subject or you don't know anything about this subject, whether you like this subject or you dislike this, but the matter of fact is that you cannot ignore this subject, because your basic survival depends on simple principle of fluid mechanics only. Your blood circulation, your breathing, all this depends on the principle of fluid mechanics. If you go for engineering applications, there are numerous engineering applications. If you have seen in the automobile, the car, the speed car basically, and if you have ever wondered that why this speed car is shaped in such a manner. If you have seen an aeroplane, the shape of the aeroplane, why that aeroplane is shaped in such a manner? What are the roles of wings in that particular aeroplane? What are the roles of the fan in helicopter? Why the shape of ship or submarine is like this? Or why the ship, in spite of being so heavy, floats in the water, whereas a small pin can sink in the water? If you have seen the cricket match, a spinner throws the ball and that ball takes a turn in the air. So what are all these principles which are guiding all these phenomena? So all these things, all these answers you will get in this particular subject. So this subject is going to be very interesting for you people. So now what actually is this fluid mechanics? So what is mechanics? As I have already told you, mechanics is a branch of science which deals with forces and its effect on physical properties of the substance. And when this mechanics is applied to fluid, this becomes fluid mechanics. And what is a fluid? Fluids are the substances which can flow. To define it in a very simple way, the substance which can flow on the application of shear stress is nothing but the fluid. Now this fluid can be either a liquid, it can be either gas, or it can be a vapor. Now to define a fluid in more detail, let us differentiate this fluid with respect to solids. So what we have already studied in mechanics of solids, what happens in solids, suppose we have this solid body, and if I am applying a shear force on it, it will distort, the shape of this solid body will distort, and as soon as the shear force is removed, it will partially or fully regain its original shape. And the angle by which it distorts, the phi, which we have given the name as phi, this angle is nothing but the shear strain. So the solids can regain its original shape and it can resist shear force under static condition. And as I told you that in solids the shear stress is directly proportional to the shear strain, tau is directly proportional to phi. Now what about in liquids? So in liquids, if I am applying a shear force, the liquid will distort, the liquid will deform continuously, and it will never regain its original shape. Once I apply the force in the static fluid, it will continuously flow, it will distort continuously, deform continuously, and it will never regain its original shape. So you can call fluid as the zero memory substance. It does not have any memory what it was before. Okay, and so the fluid can resist the shear stress only under dynamic conditions. Solids can resist under static condition, fluids can resist the shear stress only under dynamic condition and not under static condition. And third thing, in fluids, shear stress is directly proportional to rate of shear strain and not the shear strain, because the shear strain is continuously changing. As I told you, once I am applying the shear force in it, this is continuously getting deformed. That means the shear strain is continuously changing. So in fluids, the shear stress is directly proportional to rate of shear strain. That means tau is directly proportional to d phi by dt. Now coming to some fluid properties. So the very first property of the fluid is density. Density is defined as mass per unit volume. That means how much mass is accommodated in the unit volume of the substance. That is nothing but density, obviously, and it will be independent of mass. Whether it be 1 kg of substance or whether it be 100 kg of substance, the density will be fixed, and the unit of this density, as we know, will be kg per meter cube. Next is a specific volume. A specific volume is the inverse of density, that is volume per unit mass, and the unit will be equal to meter cube per kg. Volume per unit mass, that means how much mass 1 kg, how much volume 1 kg of mass of the substance is accommodating, that is nothing but a specific volume. Next is the specific weight gamma. Specific weight is defined as weight per unit volume. Okay, that means gamma is equal to W by V. W can be further written as m into g, so gamma is equal to mg by v. Mass can be further written as volume into density, so this will be v into rho into g by v, and further this can be written as rho into g. Okay, and the unit, since this is weight per unit volume, unit of weight is Newton, volume, unit of volume is meter cube, so the unit of a specific weight will be Newton per meter cube. Next is specific gravity. Specific gravity is the ratio of the density of the substance to the density of a standard fluid. And what is the standard fluid in case of liquids? So the standard fluid is taken as water, whose density, as we know, at atmospheric pressure is 1000 kg per meter cube. Now in case of air, the standard fluid, in case of gases, the standard fluid is taken as air, whose density is 1.2 kg per meter cube. So with the help of this specific gravity, which is denoted by S, with the help of this S, you can determine the value of density, you can determine the value of a specific weight. How? Suppose the specific gravity of mercury is given as 13.6. If you want to determine the density, so density will be equal to density specific gravity into density of a standard fluid. Standard fluid in liquid is taken as water, whose density is 1000 kg per meter cube. Okay, so the rho, the density of this mercury will be taken as 13.6 into 1000, which is equal to 13,600 kg per meter cube. Okay, similarly, the specific weight of this mercury, gamma, will be equal to rho into g, as I told you. Okay, so the rho we have determined as 13,600 into 9.81, so this will be 1,33,416 Newton per meter cube. Okay, similarly, specific gravity of a sea water is given as suppose 1.02. So the specific weight of the sea water gamma will be equal to 1.02 into 9810, 9.81 into 1000. So this will be equal to 1,006.2 Newton per meter cube. Specific weight of kerosene is 0.8. So the density of kerosene will be equal to 0.8 into 1000, which is equal to 800 kg per meter cube. Okay, so in this way, if the specific gravity of some substance is given, some fluid is given, you can easily determine the density or specific weight of that fluid. Okay, so now you can note one thing here, S1 by S2, that means the ratio of specific gravity is equal to rho 1 by rho 2, ratio of density is equal to gamma 1 by gamma 2, which is the ratio of specific weight. S1 by S2 is equal to rho 1 by rho 2 is equal to gamma 1 by gamma 2. Next property is a very important property of fluid, and that is viscosity. Now what is viscosity? Viscosity is the property by virtue of which the fluid offers the resistance to flow. Like friction behaves in the solid, same as the viscosity behaves in the liquid. Okay, the property by virtue of which the fluid offers the resistance to flow. And more is the viscosity, less will be the velocity on the application of same force. Now how can we determine the value of this viscosity? Now suppose we have a block which is moving over a fluid with a velocity of suppose u, okay, and the distance from the fixed part to the block is suppose b, and because the fluid which is in contact with the fixed part will have the zero velocity, and because this block is moving with u velocity, the fluid which is in contact with the block will have velocity u. And the variation of this velocity is, let's suppose, linear. The velocity is continuously increasing from fixed to the plate, the moving plate. Okay, now the distance between the plates, fixed plate and the moving plate is b. The velocity of this is u. So suppose after time dt, this plate will travel a distance u into dt. Velocity into time, total distance traveled will be equal to u into dt. And during this travel, the total shear strain is suppose d theta. So this u into dt, which is distance, is nothing but b into d theta. Arc is equal to angle into radius. So this u into dt is nothing but b into d theta. Or further you can write it as d theta by dt is equal to u by b. And this u by b can be further written as du by dy, since u is nothing but the change in velocity from fixed to the moving plate, and b is the distance between the two. So this can be written as, this d theta by dt can be written as du by dy, and this d theta by dt is nothing but rate of shear strain. As I told you, this d theta by dt is nothing but rate of shear strain. And as I told you, in liquid, shear stress is directly proportional to rate of shear strain. That means tau will be directly proportional to d theta by dt. Or further, you can write tau is directly proportional to du by dy. Now, if you remove proportionality sign, it will be tau is equal to mu into du by dy, where mu is constant of proportionality. And this mu is nothing but coefficient of viscosity, or you can directly call it as dynamic viscosity. Tau is equal to mu du by dy. Mu is the coefficient of viscosity or the dynamic viscosity. Tau, as I told you, is shear stress, and du by dy, as I told you, is the velocity gradient, or you can call it as rate of shear strain, or you can call it as rate of angular deformation. And this equation, very important equation, tau is equal to mu du by dy. This is nothing but Newton's law of viscosity. And the fluids which obey this law, which obeys this Newton's law of viscosity, are called as Newtonian fluid. For example, water, for example, air. And there are certain fluids which do not obey this Newton's law of viscosity. Those fluids are called as non-Newtonian fluid. For example, paints, bloods, inks, etc. All these fluids are non-Newtonian fluid. We will get into detail of non-Newtonian fluid also. So the fluid which obeys this law, that means the fluid in which the shear stress is directly proportional to rate of shear strain, all those fluids are called as the Newtonian fluid. Now coming to this unit of viscosity. So tau is equal to mu du by dy, or you can say mu is equal to tau by du by dy. Unit of tau is Newton per meter square. Unit of u, velocity, is meter per second. And unit of dy, which is distance, is meter. Meter will get cancelled out, and you will get the unit as Newton second per meter square. Further, in terms of kg, same unit can be written as kg per meter second, since Newton can be written as kg meter per second square. So the unit of viscosity is Newton second per meter square, or kg per meter second. Okay, now 1 Newton is equal to 10 raised to power 5 dynes. So, and 1 meter, as we know, is 100 centimeter. So 1 meter square will be equal to 10 raised to power 4 centimeters square. Okay, so if I want to convert this into dyne second per centimeter square, so this will be 10 raised to power 5 dyne second divided by 10 raised to power 4 centimeters square. So this will be equal to 10 dyne second per centimeter square. And 1 dyne second per centimeter square is 1 poise. So this 1 Newton second per meter square will be equal to 10 poise. A very important conversion. 1 Newton second per meter square is equal to 10 poise, or 1 poise is equal to 0.1 Newton second per meter square, or Pascal second. So if the unit is, which is generally given in poise, if you want to convert it, just multiply it by 0.1, you will get the unit in SI, which is Pascal second. Okay, so 1 poise is equal to 0.1 Pascal second. Now coming to the dimensional formula of mu. So mu is equal to tau by du by dy. The dimensional formula of tau is ml minus 1 t minus 2, and dimensional formula of du by dy is 1 by t. So this will be ml minus 1 t minus 1. Now what actually are the causes of viscosity? Very important thing. So viscosity is basically caused by two things. First is the intermolecular force of cohesion, and second is the molecular momentum exchange. Now in liquids, the intermolecular force of cohesion is the major cause of viscosity. Why? Because as we know, in liquid we have the cohesive forces between the molecules, and as one molecule is flowing, the second molecule will apply a resisting force, will resist that flow because of the cohesive forces. So in liquids, the predominant cause of viscosity is the intermolecular force of cohesion. Now what about in gases? So in gases, the cohesive force is very less, almost negligible. So what is the cause of viscosity then? So in gases, as the molecules are moving fast, they will collide with each other and they will lose their kinetic energy, and because of this a resistive force is act. So this is called as the molecular momentum exchange, and this is the predominant cause of viscosity in gases. The predominant cause of viscosity in liquid is the intermolecular force of cohesion, and predominant cause of viscosity in gases is the molecular momentum exchange. Now a very important thing. Now what will happen if we are increasing the temperature of liquid and in temperature of gases? What will be the effect in the viscosity of the liquid and gas? So in liquid, if I am increasing the temperature of the liquid, what will happen? The cohesive force will decrease, and because the cohesive force decreases and that cohesive force was basically responsible for the for viscosity in liquids. So as the cohesive force is decreasing, so the viscosity of liquid will decrease with increase in temperature. The viscosity of liquid will decrease with increase in temperature. What about in gases? So in gases, the major cause of viscosity is the molecular momentum exchange. So as I am increasing the temperature of the gases, what will happen? Those molecules will start moving at a very faster pace, and there will be much high molecular momentum exchange. That means the viscosity will increase. So in air, in gases, viscosity increases with increase in temperature, and in liquids, viscosity decreases with increase in temperature. Very important note. You can write if you want. For Newtonian fluids, mu depends strongly on temperature and varies very little with pressure. For liquid, viscosity decreases with increase in temperature, and for gases, viscosity increases with increase in temperature. Next is the ideal fluid. Now, what is an ideal fluid? So ideal fluid is an hypothetical fluid which is having zero viscosity. The fluid which is not having any viscosity, that is inviscid fluid, or you can call it as non-viscous fluid, or you can call it as frictionless fluid. All these such words are used for the ideal fluid which is having zero viscosity. That means mu is equal to 0 in ideal fluid. Second property, they are incompressible. Incompressible means the change in volume is equal to 0, del V is equal to 0, and therefore the volumetric strain epsilon V will also be equal to 0. And what is bulk modulus? Bulk modulus is normal stress upon volumetric strain, and since volumetric strain is 0, so the bulk modulus will be infinite for this ideal fluid. Third property, the value of Poisson's ratio for this ideal fluid is equal to 0.5. And last, this ideal fluid is not having any surface tension. So these are inviscid, non-viscous, then these are incompressible, then the Poisson's ratio is 0.5, and there is no surface tension in such ideal fluid. And in fact, this ideal fluid does not exist actually. Okay, this is just a hypothetical concept of ideal fluid. In actual practice, this ideal fluid does not exist. Next, coming to the non-Newtonian fluid. Now, what is non-Newtonian fluid? As I told you, the fluid which does not obey Newton's law of viscosity is the non-Newtonian fluid. So what does it follow? So it follows a power law. So what is this power law? So the power law says tau is equal to A du by dy to the power n plus b. This law is nothing but power law. Tau is equal to A du by dy to the power n plus b, where tau is shear stress as we know. A is the multiplying constant, n is the power index, and b is the additive constant. And this b is additive constant, or you can call it as y-intercept. Okay, now for different values of A, B and N, you will get different non-Newtonian fluid. I will tell you how. The very first case, when A is equal to mu, N is equal to 1 and B is equal to 0. That means you will get what? Tau is equal to mu du by dy. Okay, and this is nothing but Newton's law of viscosity. That means you will get a Newtonian fluid. So for A is equal to mu, N is equal to 1, B is equal to 0, you will get a Newtonian fluid. And as in this case, you can see tau is directly proportional to du by dy, so you will get a straight line. Directly proportional, straight line, and y-intercept, since b is equal to 0, okay, so that straight line will pass through the origin. Next case, when A is not equal to 0, N is less than 1, but B is equal to 0. Again here B is equal to 0, that means this curve will also pass through origin. A not equal to 0, but N is less than 1. So N is less than 1, that means you will get a parabolic curve, convex from the top, okay, and this is a non-linear curve, and such fluids are called as the pseudoplastic fluid. And the example of pseudoplastic fluid is blood. If you have seen, if you have ever touched the blood, that is a pseudoplastic fluid. Okay. Next case, when A is not equal to 0, N is greater than 1, but B is equal to 0. Again B is equal to 0, that means y-intercept is 0. N is greater than 1, you will get a parabola concave from top, okay, and such fluids are called as the dilatant fluid. Okay, so all these terms are very important. If N is less than 1, the fluid was the pseudoplastic fluid. If N is greater than 1, you will get a dilatant fluid, and the example of this dilatant fluid is butter, quicksand, etc. Quicksand means what you call in Hindi as dal-dal, that is quicksand. So these are the dilatant fluid. Next case, when A is not equal to 0, N is equal to 1, but B is greater than 0. Okay, now A not equal to 0, n is equal to 1, but b is greater than 0. So because n is equal to 1, so you will get a straight line, and b is greater than 0, so you will have some y-intercept as well. Okay, so you will get the curve like this. And such fluid is called as the Bingham plastic. For example, the sewage mud, if you have seen, the drilling mud, if you have seen. So all these fluids are the example of Bingham plastic. Okay, so next case, when a is not equal to 0, n is less than 1, but b is greater than 0. So because b is greater than 0, you will get some y-intercept. N is less than 1, you will get a second degree parabola which is convex from the top, and such plastic is called as the thixotropic. Okay, and the example of this thixotropic are the printer's ink, the wall paints, all these are the example of this thixotropic fluids. Okay, next is the x-axis. X-axis means the y coordinate is 0. Y coordinate is 0, that means the shear stress is 0, and shear stress is 0. This is possible only in case of ideal fluid. So the x-axis of this graph represents the ideal fluid. Next is the y-axis, that means x coordinate is 0. X coordinate 0 means shear strain or the rate of shear strain is 0. So if the shear strain or rate of shear strain is 0, this is possible only in case of rigid solid ideal plastic. And you can note one thing, that the study of this non-Newtonian fluid is called as rheology. Study of non-Newtonian fluid is called as rheology. Next is the kinematic viscosity, which is denoted by nu. Now what is this kinematic viscosity? This is the ratio of dynamic viscosity to density. The ratio of mu, the dynamic viscosity, to rho, the density, is nothing but kinematic viscosity. Now the unit of mu, as we have seen, is kg per meter second, and unit of rho is kg per meter cube. So the unit of nu, the unit of kinematic viscosity, will be equal to meter square per second. So you can see one thing, that the unit is meter square per second. There is no kg involved, no newton involved. That means the force in this particular unit is not involved. So that's why this is called as the kinematic viscosity, because the force is not involved. So this such viscosity is called as the kinematic viscosity. So the unit is meter square per second or centimeter square per second, and 1 centimeter square per second is equal to 10 raised to power minus 4 meter square per second, and this centimeter square per second is nothing but Stoke. Okay, so this another unit of kinematic viscosity. In fact, most common unit of this kinematic viscosity is the Stoke. So 1 Stoke is 1 centimeter square per second, or you can say 10 raised to power minus 4 meter square per second in terms of SI unit. Now the significance of this kinematic viscosity. Why is this kinematic viscosity needed when we already have the dynamic viscosity? Then what is the significance of this kinematic viscosity? So the value of dynamic viscosity, as we know, is very less for air. Air is highly viscous in nature as compared to the liquids. So the value of this air, value of dynamic viscosity for air is very less. Okay, in fact such less that it is out of consideration. So that's why for air especially this kinematic viscosity is used. So we divide the dynamic viscosity by density. The density of air is also less, the dynamic viscosity is also less. So ultimately the ratio will give us a considerable term that we can consider. So this kinematic viscosity is actually used for the airs for which the dynamic viscosity is very less. So this is the significance of this kinematic viscosity. So the mu, the dynamic viscosity of water is greater than the dynamic viscosity of air, but the kinematic viscosity of water will be less than the kinematic viscosity of air, since the density of water is more, and we are dividing the dynamic viscosity with density so as to get the kinematic viscosity. So the kinematic viscosity of water is less than the kinematic viscosity of air at any temperature. Now you can note one thing, that the Seibold viscometer is used to measure kinematic viscosity. The Seibold viscometer is used to measure kinematic viscosity. Okay, now there is a question that in gases as temperature increases, option A, mu increases and nu increases. Option B, mu increases, nu increases much. Option C, nu increases, mu increases much. And option D, both mu and nu decreases. Okay, so now as we know, nu, which is kinematic viscosity, is equal to mu by rho. Now in gases, as the temperature increases, as I told you, as the temperature increases, the viscosity will increase. That means the value of mu will increase as the temperature increases. First thing. Now what about nu? Now what will happen to nu? So nu is equal to mu by rho, again the density. So what happens to density of air? As the temperature increases, the molecules of air moves far apart, so the density of air decreases. Okay, so nu is equal to mu by rho. Since mu is increasing and rho is further decreasing, therefore nu will increase much. Okay, so the answer should be B, that mu increases and nu increases much. Next term is the compressibility. Now what is compressibility? Compressibility is the susceptibility to change in volume. That means how easily a substance, the volume of the substance can be changed. That is called as compressibility. Now we have seen one property of bulk modulus K, which is equal to normal stress upon volumetric strain. Now suppose if a component is subjected to force dP from all sides, so the bulk modulus will be equal to dP upon dV by V, and since the volume is decreasing, as we are applying a negative force, compressible force, so the volume will decrease, so this bulk modulus K will be equal to minus dP upon dV by V. Okay, further in terms of density, since density is increasing, as we are compressing, density will increase, so this can be written as dP upon d rho by rho, positive, because density is increasing. Okay, so this K is equal to dP upon d rho by rho. Now compressibility is just the inverse of this bulk modulus. Compressibility is equal to 1 by K. Okay, so this K is equal to rho dP by d rho. So this compressibility will be equal to 1 by rho into d rho by dP. So this is the formula for compressibility, 1 by rho into d rho by dP. So I am pretty sure all of you have played with such toys in your childhood, and if you have ever wondered that why such shapes, this bubble, the shape of these bubbles are spherical only. I mean this, if you can see this closely, this is oval in shape, but finally when I blow this, finally this becomes a spherical shape. Or if you have seen the water droplet, the raindrops are always spherical in shape. If you leave the water in a random shape in the atmosphere, finally it will become spherical. So what is the reason behind that? So the reason is the surface tension. So what actually is the surface tension, that we are going to study now. Suppose we have this beaker in which the water is filled, and we are considering two different points here. The first point, point A, is taken inside the water, and second point, point B, is taken at the interface of water and air. Now this point A is surrounded by the liquid from all the sides. So the cohesive force will act from all the sides, the equal cohesive force will act from all the sides, which will balance this. Now what about point B? So this point B is at interface of two liquids, and since the forces acting at the interface will be different, forces acting, cohesive forces acting in liquid will be different as that of in air. So at point B only the net downward cohesive force is acting. So that's why because of this there is an unbalanced line force which is acting at the interface of the two fluids. This unbalanced line force, why this unbalanced? Because only downward force is acting, not upward. So this unbalanced line force is nothing but the surface tension. So because of this surface tension, you will get the surface of this liquid like this. And why the ends are like this? Because of the adhesive force. And liquid water is a wetting fluid. Wetting fluid means the adhesive force is more than that of the cohesive forces. Okay, so the interface of water, the boundary of water and air will be like this. So this is nothing, this is basically because of the surface tension. So the surface tension is actually the line force per unit length. This is denoted by sigma. So this sigma will be equal to F by L. Or you can also define it as surface energy per unit area. Surface energy per unit area. Surface energy means F into L divided by area, which is L square, and this will be equal to F by L. So this is nothing but the surface tension, and as I told you, it arises because of the two types of forces, cohesive forces and adhesive forces. Now what happens when the temperature increases? So as the temperature increases, obviously the cohesive force of the liquid decreases. So as the cohesive force decreases, so the surface tension will decrease. Because majority of the scientists neglect the effect of addition and consider that the surface tension is only because of cohesion. So as the temperature increases, cohesive force decreases, so the surface tension also decreases. Now I have told you there are various applications of this surface tension. Suppose I am leaving an irregular shape of water in the atmosphere. finally it will turn into the spherical droplet. Now why it is happening? This is because of surface tension. Now because that surface tension will try to bring that droplet into the minimum surface area, that is unbalanced force, unbalanced line force, that will try that the surface area of that droplet should be minimum, and that is only possible in a spherical shape. So that is the reason why the bubbles or the water droplet, all these are spherical in nature. Next is the hydrostatic excess pressure or the gauge pressure inside a bubble. So suppose we have any bubble, so how much excess pressure is inside the bubble? Del P is equal to 8 sigma by D, or you can say 4 sigma by R. Now inside a water droplet, this del P is equal to 4 sigma by D, or you can say 2 sigma by R. Now for a hemispherical droplet, this del P will be equal to 2 sigma by D, or you can say sigma by R. Next is the capillarity. What is capillarity? The rise and fall of the liquids in the tube of a smaller diameter. Smaller diameter means diameter less than 10 mm. This is called as capillarity. Now basically there are two types of fluid. First type of fluid is the wetting fluid, and second is the non-wetting fluid. Wetting fluid, for example water. Wetting fluid means in which the adhesive force is more than that of the cohesive force. Okay, suppose I am dropping a water on a surface, it will wet that surface, because the adhesive force of the water, that means the force between water and the surface, is more than that of the cohesive force inside the water. So that wets the surface. On the other hand, if I am dropping a mercury on the surface, it will not wet the surface, because the cohesive force of the mercury is more than that of the adhesive force. Okay, so for these two fluids, for wetting fluid and for non-wetting fluid, we will consider this capillarity. So for suppose a wetting fluid is there, a water is there in a beaker, and I am pouring a pipe on it and dropping a pipe on it. So what will happen? So because of the surface tension, the level of water will rise in this pipe. Now because this is a wetting fluid, the level will rise. Okay, suppose the level rises by a height h. Okay, and the surface, as I told you, in the surface tension, because this is a wetting fluid, so the surface will, the curve will be like this, and the angle which the tangent of this curve is making with the tube is nothing but theta. Okay, now in case of non-wetting fluid, in case of mercury, what will happen? So now in non-wetting fluid, if I am dropping a pipe in it, so the level of mercury will fall and the surface will be like this, because this is non-wetting fluid. That means the cohesive force is more than that of the adhesive force, so the surface will be convex from when look from the top. In case of water, the surface will be concave when look from the top. Okay. So this height h is equal to 4 sigma cos theta upon gamma into d, where d is the diameter of the pipe, and this capillarity, as I told you, is both because of cohesion and adhesion. Okay, now what happens when the temperature increases? So as the temperature increases, the cohesion will decrease. So as the cohesion will decrease, surface tension will decrease, and finally the liquid will drop. The height of the liquid will decrease. Now the value of this theta, the theta, as I told you, for the pure water and for clean glass, the value of theta is 0, and thus for pure water and clean glass, h is equal to 4 sigma divided by gamma into d. Or you can say this height is inversely proportional to diameter, h is inversely proportional to d, or you can say h2 by h1 is equal to d1 by d2. That means as diameter increases, the height will decrease. Now you can, in further units we will study about this. In pressure measurement, obviously you cannot use the tube below 10 mm, because in pressure measurement what you do is you just put the tube and you read the height, and based on that height you calculate the pressure. But in this capillary tube, the rise in the tube is because of capillarity and not because of the pressure difference. Okay, so in pressure measurement, in barometer, the tube which is used should be, the diameter of that tube should be at least greater than 10 mm, so as to avoid the height rise because of capillarity. Now next phenomena is the vapor pressure. Now what actually is this vapor pressure? So I will tell you with the help of one example. Suppose we have a closed beaker in which I am having some water up to a certain level, and I am heating this water. So what will happen? Because the beaker is closed, I am heating this water, so the water will start evaporating. Okay, and at a certain point the air which is inside that beaker, the left air which is inside that beaker at a certain point will be saturated completely. That means it cannot absorb further vapor anymore, and after this if I continue to heat, then after that it will get condensed and it will start returning to the water itself. So this is an equilibrium condition. The amount of fluid which is getting evaporated will be equal to the amount of fluid which is getting condensed. So the pressure at this particular point is called as the vapor pressure. The pressure which this vapor is applying on the fluid, that pressure is nothing but the vapor pressure. Okay, if I consider a vacuum, initially the free space, if I consider it as vacuum, so whatever pressure I am getting is the vapor pressure. Otherwise, if the air is there, then the partial pressure is taken as the partial pressure of vapor is taken as the vapor pressure. Now, it is not essential that you should heat this, because the evaporation already occurs, because heating just increases the rate of evaporation. If you have seen a water bottle which is kept in for few days, you have seen certain droplets in the free air side. Okay, so that is because of this, because the vapor, because the water is getting evaporated, and after a certain point it is also get condensed. Okay, so that point is called as the equilibrium point, when the rate of evaporation is equal to rate of condensation, and the pressure which that vapor is applying on that water at that particular point is called as the vapor pressure. Now, a very important thing, that the vapor pressure of mercury is almost negligible. Mercury is having almost zero vapor pressure. Water is having some vapor pressure, and this is the reason why mercury is used in the barometer, because in barometer we have the tube, and inside that tube we have the mercury, and suppose if we are having certain vapor pressure of mercury, then we will have to consider the vapor pressure as well. Now, in order to get the total pressure, we will have to add the vapor pressure as well as the pressure because of that height of mercury. So that will become a complicated task. So that's why the mercury is used, because if we use the water, we will have to calculate the vapor pressure of water as well. So that is the first reason why mercury is used, because the vapor pressure of mercury is almost negligible. That means you can consider almost vacuum at the at that free space. Now, the second reason why mercury is used is because the density of mercury is very, very high. Okay, and as we know, P is equal to rho GH. All these things we will study in the fluid statics. I am just telling you why mercury is used. So, because P is equal to rho GH, so if the density is high, the height should be less. The height is considerable. If we use water, the height of water column will be very, very high. So, these are the two reasons why mercury is used as the barometric fluid. Next process is cavitation. Now, what actually is this cavitation? Suppose a liquid is flowing through a pipe, and suppose it passes through a low pressure region. So, what actually happens when it passes through a low pressure region? The dissolved liquids will vaporize and form a bubble there. Now, why does the dissolved liquid will have the bubble? Because as we know that as the pressure decreases, the saturation temperature also decreases. So, there are certain liquids whose saturation temperature may be at the temperature of atmosphere, so they will bubble up. At lower pressure they will form the vapor and they will form the bubbles. Okay, so such bubbles, when they reach the high pressure region, okay, when the same liquid reaches the high pressure region, again that bubble will get bursted and it will start hitting to the surface of the pipe, and this process is called as the pitting. Okay, and this process, the process of formation of bubble, is called as cavitation, and when the bubble bursts and it starts striking the surface, that process is called as the pitting. Okay, so what are the effects of this cavitation? First, it produces lots of noise. Okay, the efficiency of the flow will have a sharp fall and it will damage the adjoining surface of the pipes. Now, suppose you get the question that the cavitation is due to option A, vapor pressure, option B, low pressure, option C, low vapor pressure, option D, high pressure. Okay, so the answer should be B, that is low pressure. That is not because of low vapor pressure. Cavitation is because of low pressure. Another question, arrange the vapor pressure of kerosene, mercury, water and petroleum in ascending order. Ascending order. Okay, so the lowest vapor pressure is of mercury, then of water, then of kerosene, and highest vapor pressure is of petroleum. Next is the continuum concept. Now, what this continuum concept is? Continuum concept assumes that there is a uniform distribution of molecules throughout the substance, throughout the liquids or throughout the fluid. Okay, and the liquid follows this continuum concept more as compared to that of the gas, because in liquids we have the cohesive forces. Okay, so they are already joined with each other, so there is a uniform distribution of molecules throughout the liquid, so the liquid follows the continuum concept. Now there is a number called as the Knudsen number. Knudsen number is the ratio of mean free path to the characteristic length of the fluid. And this Knudsen number actually describes how far is our fluid from the continuum concept, from following the continuum concept. The mean free path you can define, suppose the two molecules are colliding with each other. So the distance between the two just before they collides with each other is called as the mean free path. So the ratio of this mean free path to the characteristic length is nothing but the Knudsen number. Okay, and this mean free path obviously in liquid is 0, so the Knudsen number in liquid will be 0. And the more will be the Knudsen number, less continuous the substance, the fluid will be.